Okay, so we have to have this template, the Lawvere monoid theory, that has objects corresponding to these powers of M. But how do we know that these are powers of M? What kind of structure does this category have to have? So, in order for M squared to be the square of M, right, 2 has to be the square of 1, right? So 2 has to be equal to 1 cross 1, in a sense. And then we can say, well, these models or these functors are special functors, right? They preserve product. So if we start with a tower of power here, right, then a product preserving functor will map it into a tower of power here. So that's all we need. We need to say our models are product preserving functors. Okay? So it means that there is a certain structure of morphisms here. Because what does it mean for 2 to be a product of 1 times 1? It means that 2 has to have projections, right? There have to be like 2 morphisms that correspond to first and second projection, right? So this functor will map these 2 morphisms into first and second here. Here, this is set, so this is really first and second. So these are the 2 projections from a Cartesian product, right? And of course, this has to be like the best of these projections. I mean, if you remember how products are defined, they are defined using this universal construction. It means that any other candidate for a product can be factored out using this. So we will need all these other morphisms that factorize other products and so on. So this is this forms a template in which we actually have 2 structures, right? One structure is the one that defines powers or products. Right? So this is a structure that says there are projections from 2 to 1, there are projections from 3 to 2, from 3 to 1. There are also some morphisms from 0, like this is supposed to be a terminal object, right? 0 is supposed to be the terminal object here because it has to map into a singleton set. So it means that it has to have unique morphisms to every other object, right? So it has to have these morphisms going up like this and so on, right? So all this basic structure, there's this basic structure that just defines products and the terminal object. And this basic structure is sort of, well, not sort of. This basic structure has to exist for any algebra, not only for monoid. Like if we wanted to have a Lawvere theory of groups or rings or whatever else, right, we'll have to have this structure. As long as we are interested in having these operators here, right, these are, we have to start with this basic structure. But then the theory of monoids will have some additional morphisms that make it into a monoid, right? So there will be, besides these projections, these projections are sort of trivial, there has to be something that multiplies 2 elements to get a third element. Our monoidal multiplication, that's a different thing, right? This is very specific for the monoid. There has to be also something that goes from 0 to, did I say this is a terminal object?
Mm-hmm.
Right. So these go the opposite direction, right? Terminal object has morphisms going into it. It's terminal, right? Okay. So this morphism that defines unit for a monoid goes in the opposite direction. That's important. Okay? I mean, there's always these morphisms that go into 0 because it's a terminal object, but for monoid there is this one. Like if we were defining a group, then there would be also a special one going from 1 to 1, and so on, right? So this Lawvere category, this category that forms a template for the monoid, right? It has really two separate structures. Well, they are intertwined, right? But one of them is common to all algebras, and another is particular for this algebra, for monoids. Okay? So can we go even further, asks Lawvere, right? It's like, can we separate this common structure out of this? So a common structure would be, it's like, we'll have yet another category here in which we just have 0, 1, 2, and so on, and we'll have the projections, right? And we'll have, this is the terminal object, so we have this, right? And so on. So this would be like the skeleton for every Lawvere algebra, right? So we are just like abstracting more and more and more. So we would have this thing, which maps into this thing and generates the tower of power. Then on top of this, we have these additional morphisms that will define multiplication, unit, and so on, right? And that will be our monoidal theory. And then we'll have these models, and each model will generate a different monoid instead. Okay? So there will be models that, first of all, they will pick a different carrier, right? Because it depends on what 0 is mapped. 1 is mapped into the carrier. So for every functor, every product-preserving functor from L-mon, we'll pick one carrier. But even after picking the carrier, there is still a freedom of mapping these morphisms, right? And there will be a different monoid for integers here when we define addition, and a different one if we do multiplication, right? So these are two different monoids, but they have the same carrier. So the difference between them is that there is a different functor. This functor will, a functor collapses some of the morphisms. In principle, it could collapse certain morphisms. It will say, well, here these are two separate morphisms, but here I'm mapping them into the same morphism. They cannot split morphisms, right? But they can collapse them. So different ways of collapsing these morphisms, even for the same carrier, will produce different monoids. And that's important, right? Another thing that's important here is when I say it's product preserving. What do I mean by product preserving? It actually should not preserve the product on the nose. What does it mean? See, there is an object 3 here. This object 3 can be obtained in many ways. It can be obtained as a product of 1 cross 1 cross 1. Or it could be obtained as 2 times cross 1 or 1 cross 2, right? There are many ways of obtaining object 3 in set. Well, actually, but they are all equivalent to object 3 in L. There's only one object 3. So they all have to collapse into object 3. But in set, they are different. Okay? Because in set, product is not associative. It's associative up to isomorphism. Okay? This is very important. It's associative up to isomorphism. A pair of A, B, comma, C, I've said this many times, but I will keep repeating this. It's not the same as a pair A, B, C. But they are isomorphic. Right? We know this in Haskell. If you have a function that accepts this, it will not accept this. It will not type check. However, these are isomorphic. They contain exactly the same information. You can convert one to another using a function, trivial function, but still, it's not the same. Okay? So it's very important that these product-preserving functors actually preserve multiplication, preserve product up to isomorphism. Okay? So this is product preserving PP up to iso. Okay. Okay. All right. So now let's talk about this. Okay. So this is the skeleton of this thing. And we could say, okay, well, how can we construct this? Well, we have to construct these, like, starting with element 1, we'll have to construct products, the 0th power, the 2nd power, 3rd power, and so on. Turns out that it's much easier to describe the dual category, the opposite category to this, where instead of products, we'll have sums. Okay? So 0, it's like, what's the opposite of this? The opposite of 0 would be, this is a terminal, so it would be an initial object, right? So it's an initial object that has morphisms to every other object, unique morphisms to every other object. There is an object 1, right? Abstract, totally abstract object 1. There is an object 2, which is equal to coproduct 1 plus 1. And there's an object 3 that's 1 plus 1 plus 1. Okay? And so on. Addition is simpler than multiplication. So this category is sort of like a logarithm of this category, because it replaces multiplication with addition, right? This is how you can remember this. Now this category actually is almost the same as the category of finite sets. Okay, there is this category fin set of finite sets. So a category of finite sets can be, well, first of all, it has an empty set. That would be our 0. It has a singleton set. And then every other set can be formed as a sum, right? So as 2-element set is just a sum of 2 1-element sets, right? It's a union, disjoint union, right? So using disjoint union, which is the coproduct in this category of sets, using disjoint union, you can generate the whole category of finite sets. The only problem with this, a tiny problem, is that fin set has multiple objects for 2, 3, 4, and so on. Why? Because coproduct or disjoint sum, disjoint union, is again not associative. So Right? 1 plus 1 plus 1 is not exactly the same as 1 plus 1 plus 1. The same problem I mentioned there, but it's the same problem with addition as with multiplication. It's not associative. It's associative up to isomorphism, of course. I mean, these two sets are isomorphic. They have 3 elements, you know, it's like, right, you can just find an isomorphism between them easily. But thin set has more objects than we need. What we need is a category in which we have only one object 2, and a single object 3, single object 4, and so on. How do we construct a category like this? Well, there is a very simple construction in category theory. For any category, you can define a new category that's called the skeleton of this category. The skeleton of a category is the same category in which all the objects that are isomorphic are collapsed to a single object. Okay? So all these guys, 1 plus 1 plus 1, and 1 plus 1 plus 1, they are collapsed into the object 3. Okay? So we just identify all objects that are isomorphic. Now this might seem like, okay, we are going through so many motions, right? But what is important is that the starting point, the thin set thing, okay, that this is a very well understood category because it's a category of finite sets. We know everything about this category. We know every single function. Morphism is a function there. We know every single function going from, let's say, a 2-element object to a 3-element object, right? You can list them, right? Well, it just means picking 2 elements out of 3 elements, right? 3 to 2, well, picking, you know, collapsing some elements into 2, and so on, right? So it's like all permutations of a selection of elements, permutations, and so on. So this is something that we have full control over. This is our assembly language. We know this assembly language, right? Very well. So we make these small steps that lead us from thin set to our monoid in small increments. So we start with the category thin set. Okay, so in the category of thin set we have this object 0, which is the initial object. We have the object 1, which is a singleton, right? We have a bunch of objects 2. Well, so we have, you know, we have 1 plus 1. We have object, well, 1 plus 1, and we have object 2, and we have object 1 plus 1 plus 1, and the object 3, and okay, right? Now you take a skeleton of this, and we call it F. The skeleton of this will have 0, 1, 2, 3. Plus all these morphisms. So this is the initial object, so it has this, right? So we'll have this. This is a sum of these, so it will have 2 injections, right? Left injection, right injection. You know, and there will be some injections here, and so on. But this is all inherited from thin set. Okay? Just by collapsing these objects, these morphisms still remain, right? But they go between these collapsed objects. So we know how to construct this. Now we go to F up, the opposite category. And these sums suddenly become products. And this gives us this tower of power that we need, right? So there will be we reverse every arrow here. Right? Every arrow is reversed. And so on. And this defines just object 1, the terminal object, object 1, and the powers of 1. Right? And this is all the objects that there are. And all the products are defined in this. Then we go to Lawvere theories. And now there can be many Lawvere theories, but in particular we are interested in the Lawvere theory for monoids. And the Lawvere theory of monoids will inherit, okay, so now we have a functor which is called IL, I think, that maps f op to this Lawvere algebra, which is, this functor maps objects one-to-one. So Lawvere category does not contain any more objects. It contains just these objects, 0, 1, 2, 3, and so on. It inherits all of these morphisms, right? So this is a product preserving. So f op has product. F had sums. This one has coproducts. This has products. This one inherits all the products nicely. So all the black arrows are still here, right? And now I guess I should add blue arrows, okay? And this part is specific for the monoid. So it will have this, it will have this. In fact, this is the interesting one, okay? There are many of these, you would think that there's a single one, but actually there are many of these, okay? We'll get to this in a moment. But I want to finish this picture. And finally, we have set, okay? And then we have product preserving up to isomorphism, product preserving functors, which we call models of the Lawvere theory or Lawvere algebra. So 1 is mapped into some carrier M. This is mapped into M squared because it preserves products. So 2 is mapped into M squared. You know, all these black arrows are still present there. This is mapped into a singleton set, right? This is mapped into our unit, monoidal unit. These guys might be collapsed. Not all of them survive this, right? Some of them are collapsed into a single one. Like, you know, 3 times 2 is the same as 2 times 3, for instance. Well, it's just a law for multiplication. Okay, and this is called a model, this functor. So things are splitting now, right? So this is, f op is just a single category. For all Lawvere theories, this is the same f op. Then it splits into many different Lawvere theories, each of them describing a different algebra. So there's a different for monoid, there's different for group, and so on. Then for each of them, it splits into many, many models of this theory inset. Okay? So it creates this very nice levels of abstraction. What is the common thing between all monoids? Oh, this is the common thing for all monoids. What's the common thing for all algebras? Well, f op is the common thing of all algebras, and so on. Okay? Now let's talk about this. So this, if this is So this is like L-mon going from 2 to 1, okay? The home set from L-mon to 2 to 1. Okay, so what kind of functions? So this home set will be mapped into functions from m squared to m. So these are functions of 2 arguments, okay? So these are functions of the type f of x, y, right? Where x and y are elements of the monoid. How many different functions do we have of 2 arguments that are work on a monoidal? Well, what can we do with this? Well, there is one function that will just give us empty, right? So these 2 are elements of a monoid, right? And they have to return an element of a monoid. So one possibility is they just return empty. Okay, the empty one, this comes from the skeleton. It's already there. It's not very interesting. Then there is one that returns x, and there's one that returns y. Well, these are the 2 projections, right? So they are also in the skeleton. It's this one and this one, right? The others are interesting. Well, so what can we say? Well, we have one that says, okay, x times y. That's the interesting one, right? It multiplies them using the monoidal multiplication. There is one that does y times x. So I'm using this for monoidal multiplication, right? It's like in Haskell. There is one that says x times y times x. Okay. What else can I say? I can produce lots of these, you know. So I can start with y. I can put another y here. I can put an x here, and so on. You see what I'm doing? Some of them are the same, probably. But when I'm creating a general theory, then I have to have separate morphisms on this side for them. Some of them might collapse when I do a model. But one of the models is actually the free monoid. And this free monoid does not collapse any of these guys, except for the ones that satisfy the laws. Okay? So in principle, all these modular laws have to be there. Which means there are as many functions in L-mon 2.1 as there are lists of 2 elements. Okay? So these are just lists of 2 elements, right? I'm just putting this multiplication between them, but this is list. So this is really a free monoid F-mon of 2 elements. Okay? So that's interesting. So this is the structure of these blue arrows. Well, blue and black as well, right? Because like, we also have this x and y. And we also have empty, so there's also this one. Okay. So next time, we'll go deeper into this, okay? There is much more stuff to Lawvere theories, okay? So let's take a break here.